NENOMATICA, where mathematics meets YouTube excellence. Welcome to this math video. Today we're going to explore an interesting algebraic proof. Let's look at our example. We need to prove that if a squared equals 2a plus 1, then a to the fifth equals 29a plus 12. Let's work through this step by step. Let's start by rewriting a to the fifth. According to the exponent rule, a to the fifth equals a times a to the fourth. Now, let's rewrite a to the fourth. Using the power rule, a to the fourth equals a squared squared. Now comes the key step. We can substitute the given identity a squared equals 2a plus 1. So a to the fifth equals a times the quantity 2a plus 1 squared. Next, we need to expand the square of the binomial 2a plus 1. Using the binomial theorem, the quantity 2a plus 1 squared equals 4a squared plus 4a plus 1. Now we need to substitute a squared again. Remember, a squared equals 2a plus 1 from our original identity. So a to the fifth equals a times the quantity 4 times the quantity 2a plus 1 plus 4a plus 1. Let's simplify the expression inside the brackets. 4 times the quantity 2a plus 1 equals 8a plus 4. So a to the fifth equals a times the quantity 8a plus 4a plus 1, which equals a times the quantity 12a plus 5. Now, let's distribute the a. Using the distributive property again, we get a to the fifth equals 12a squared plus 5a. Finally, we substitute a squared one more time. Since a squared equals 2a plus 1, a to the fifth equals 12 times the quantity 2a plus 1 plus 5a. Let's expand this expression. 12 times the quantity 2a plus 1 equals 24a plus 12. So a to the fifth equals 24a plus 12 plus 5, which equals 29a plus 12. Therefore, we have proven that if a squared equals 2a plus 1, then a to the fifth equals 29a plus 12. Today, we'll be solving an algebra problem that uses the squared binomial identity. Let's start by examining our given equation. We have 3x plus 1 over 2x equals 4, and we need to find 9x squared plus 1 over 4x squared. At first glance, there doesn't seem to be a direct connection between these expressions. But notice that our target expression contains squares of terms that appear in our original equation. This suggests we might use the squared binomial identity. Let's apply the squared binomial identity. This identity states that the square of a sum equals the square of the first term plus twice the product of the terms plus the square of the second term. Let's square both sides of our original equation. Now, we'll expand the left side using the squared binomial identity. If we let it equal 3x and b equal 1 over 2x, then a squared is 9x squared, and b squared is 1 over 4x squared. For the middle term, we have 2 times a times b, which is 2 times 3x times 1 over 2x, which simplifies to 3. Let's simplify the middle term. 2 times 3x times 1 over 2x equals 2 times 3 halves, which equals 3. So our equation becomes 9x squared plus 3 plus 1 over 4x squared equals 16. Now, to find 9x squared plus 1 over 4x squared, we need to subtract 3 from both sides of the equation. This gives us 9x squared plus 1 over 4x squared equals 16 minus 3, which equals 13. Therefore, the value of 9x squared plus 1 over 4x squared is 13. Slide and let's summarize what we've learned. We started with the equation 3x plus 1 over 2x equals 4, and we needed to find the value of 9x squared plus 1 over 4x squared. The key insight was recognizing that we could use the squared binomial identity to relate these expressions. We squared both sides of the original equation, expanded using the identity, simplified, and then isolated our target expression. As practice, try applying this technique to similar problems where you need to find expressions involving squares of terms that appear in a given equation. Let's look at our problem. To solve this problem, we need to find the value of x plus 1 over x first, and then take the square root. Let's recall a useful algebraic identity x plus 1 over x equals x squared plus 1 all over x. So let's write x plus 1 over x as x squared plus 1 over x. Now, we need to substitute our given value of x equals 2 plus the square root of 3 into this expression. we get x plus 1 over x equals the quantity 2 plus the square root of 3 squared plus 1, all divided by 2 plus the square root of 3. Let's expand the expression in the numerator. We can use the binomial expansion formula. A plus b squared equals a squared plus 2ab plus b squared. So 2 plus square root of 3 squared equals 2 squared plus 2 times square root of 3 plus square root of 3 squared. This gives us 4 plus 4 times square root of 3 plus 3, which simplifies to 7 plus 4 times square root of 3. Now, let's add 1 to our expanded expression. 7 plus 4 square root of 3 plus 1 equals 8 plus 4 square root of 3. Looking at our numerator, we can factor out a 4. Let's recall that we can factor out common terms from an expression. So 8 plus 4 square root of 3 equals 4 times the quantity 2 plus square root of 3. Now we can simplify our fraction. Using the property that if the numerator and denominator have a common factor, we can cancel it out. Our expression becomes 4 times the quantity 2 plus square root of 3 divided by 2 plus square root of 3, which simplifies to just 4. Now we can take the square root of 4 to find the value of the square root of x plus 1 over x. The square root of a number is the value that, when multiplied by itself, gives the original number. Therefore, the square root of x plus 1 over x equals the square root of 4, which equals 2. Therefore, our final answer is 2. Let's summarize what we've learned. Welcome to our technical mathematics video. Today, we're going to solve a complex algebraic expression step by step. Let's start with our example. We need to find the value of a in the following expression. A equals the square root of the product of 61 times 63 times 65 times 67 plus 16 minus 122. We're given that x equals 61. Let's substitute this value and see what we can determine. Let's expand the expression x times the quantity x plus 2 times the quantity x plus 4 times the quantity x plus 6 plus 16. Next, we'll regroup the terms to make the expansion easier to handle. We can write this as the quantity x times the quantity x plus 6 times the quantity x plus 2 times the quantity x plus 4 plus 16. Now, we expand each subexpression. X times the quantity x plus 6 equals x squared plus 6x. And the quantity x plus 2 times the quantity x plus 4 equals x squared plus 6x plus 8. We also introduce a substitution where x squared plus 6x equals t. Using our substitution, we can rewrite the expression as t times the quantity t plus 8 plus 16. Expanding t times the quantity t plus 8, we get t squared plus 8t plus 16. We can recognize that t squared plus 8t plus 16 is actually equal to the quantity t plus 4 squared. Now, we substitute back the original expression for t, which gives us the quantity x squared plus 6x plus 4 squared. Let's go back to our original problem. We now need to calculate a for x equals 61. First, we have x equals 61 and the expression x times the quantity x plus 2 times the quantity x plus 4 times the quantity x plus 6 plus 16. Using our derived result, we know that this expression equals the quantity x squared plus 6x plus 4 squared. Therefore, a equals the square root of the quantity x squared plus 6x plus 4 squared minus 122. The square root of a perfect square is simply the expression inside, so the square root of the quantity x squared plus 6x plus 4 squared equals the absolute value of x squared plus 6x plus 4. Since x equals 61, which is positive, we don't need the absolute value. We can simplify further to get a equals the square root of x squared plus 6x plus 4 minus 2x. This simplifies to a equals the square root of the quantity x plus 2 squared. Therefore, a equals the absolute value of x plus 2. Since x equals 61, a equals the absolute value of 61 plus 2, which equals 63. Let's summarize what we've learned in this technical mathematics exercise. First, we identified the complex expression involving a product of consecutive terms. Second, we used algebraic manipulation to transform it into a perfect square form. Third, we simplified the nested square roots by applying the property that the square root of a perfect square is its absolute value. Finally, we calculated the exact value of a to be 63. This problem demonstrates important algebraic techniques, including factorization, substitution, and recognizing special patterns like perfect squares. Thank you for watching this technical mathematics video. Practice similar problems to strengthen your algebraic manipulation skills. Until next time. Welcome to our mathematics lesson. Today, we'll be exploring the concept of the golden ratio and solving a specific problem related to it. The golden ratio is a special number found by dividing a line into two parts so that the longer part divided by the smaller part is equal to the whole length divided by the longer part. Let's start by understanding what the golden ratio is. We say that a positive number t is a golden ratio if it satisfies the equation t squared equals t plus 1. We can visualize this with a simple diagram. Imagine we have a line divided into two segments, where the ratio of the longer segment to the shorter segment is the same as the ratio of the whole line to the longer segment. Now, let's examine our specific problem. We're told that for a positive number t that satisfies the golden ratio equation, t squared equals t plus 1, we need to calculate the value of t to the power of 5. Let's solve this problem step by step. First, we need to find a pattern that will help us calculate higher powers of t. Let's square both sides of our original equation. When we square both sides of t squared equals t plus 1, we get t to the power of 4 equals t plus 1 squared. Now, let's simplify this expression by substituting the original equation. Since we know that t squared equals t plus 1, we can substitute this into our equation. This gives us t to the fourth power equals t plus 1 plus 2t plus 1, which simplifies to t to the fourth power equals 3t plus 2. To find t to the fifth power, we'll multiply both sides of our equation by t. Let's multiply both sides of t to the fourth equals 3t plus 2 by t. This gives us t to the fifth power equals 3t squared plus 2t. Now, we'll substitute t squared equals t plus 1 again to simplify our expression further. Let's replace t squared with t plus 1 in our equation. This gives us t to the fifth power equals 3 times t plus 1 plus 2t, which simplifies to t to the fifth power equals 3t plus 3 plus 2t. And finally, t to the fifth power equals 5t plus 3. Therefore, we found that t to the fifth power equals 5t plus 3. We can verify this result by checking it against the known value of the golden ratio, which is approximately 1.618. If we calculate 5 times 1.618 plus 3, we get approximately 11.09. And if we calculate 1.618 to the fifth power directly, we also get approximately 11.09, confirming our answer is correct. Let's summarize what we've learned. We solve for t to the fifth power when t is the golden ratio, which satisfies t squared equals t plus 1. We found this by first squaring both sides of the original equation, then substituting known values, multiplying both sides by t, and finally substituting again to get our answer. T to the fifth power equals 5t plus 3. For practice, you might t to the fifth power equals 5t plus 3. For practice, you might want to try finding other powers of t, such as t cubed or t to the sixth. The golden ratio appears in many areas of mathematics, art, and nature, so understanding its properties is valuable in many contexts. As a bonus, let's look at a three-dimensional visualization of the golden ratio. The golden ratio is often found in three-dimensional objects in nature and design. Here we're creating a golden rectangle where the ratio of the longer side to the shorter side is the golden ratio, approximately 1.618 to 1. When we extend this to a three-dimensional box, we get what's called a golden cuboid. These shapes are considered aesthetically pleasing and are often used in art and architecture. Thank you for watching this lesson on the golden ratio. Welcome to our math video. Today, we're going to explore the geometric meaning of the algebraic identity, the square of a sum. Specifically, we'll see that a plus b squared equals a squared plus 2ab plus b squared. Let's visualize this identity using a geometric approach. We'll start with a square that has sides of length a plus b. The area of this square is the length times the width, which is a plus b times a plus b, or a plus b squared. Now, let's divide this square into parts. We'll split the square vertically at distance from the left side, and horizontally at distance from the bottom. This gives us 4 regions that we can analyze separately. Let's label these regions based on their areas. Let's analyze the area of each region. The bottom left region has width a and height a, so its area is a squared. The bottom right region has width b and height a, so its area is a times b. Similarly, the top left region has width a and height b, so its area is also a times b. Finally, the top right region has width b and height b, so its area is b squared. Now, let's add up all these areas to get the total area of the square. We have a squared from the bottom left, plus AB from the bottom right, plus another AB from the top left, plus B squared from the top right. So the total area is a squared plus 2 AB plus B squared. But we already know that the total area is a plus B squared. Therefore, a plus B squared equals a squared plus 2 AB plus B squared. Let's recreate the diagram shown in the problem. Here, we have a square with side length a plus B. It's divided into 4 regions. A squared in pink, 2 regions of AB in yellow, and B squared in green. The square identity is visualized by breaking down the large square into these 4 smaller regions. The total area can be written as either a plus B squared, which is the area of the whole square, or as the sum of the 4 regions. A squared plus 2 AB plus B squared. Quick challenge. Let's see if you can try this on your own. What if we have a minus B squared instead? Try to visualize and figure out what a minus B squared equals. Pause the video and think about it. The answer is a squared minus 2 AB plus B squared. The approach is similar, but the signs change because we're subtracting B instead of adding it. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.